Hello everyone. Okay, so you'll notice that this PowerPoint's a little bit different from the previous PowerPoints we've been using. Our publisher content is way too detailed. So when we're talking lymphatic system, immune system, unless you're going to go into super specialized medicine, then you'll have plenty of classes to really dig into the system. We're going to use this different PowerPoint from a different publisher and just talk about what you'll need to know for our class and the things that you guys are going to go on to do. All right, so the lymphatic system is comprised of three parts. It's a network of lymphatic vessels. We just call these lymphatics. You'll see them as both. Lymph is the liquid part only, and then lymph nodes, you've probably heard of these, and you've probably heard of these in terms of cancer. So has the cancer gotten into the lymph nodes yet? And that's kind of what we'll touch on today. We'll talk about all of these parts of the lymphatic system, and then we're going to end with the immune system. So what does the lymphatic system do, or the lymphoid system? Both of them mean the same thing. Semantics, different ways of saying the same thing. So throughout this, you'll see both lymphatic and lymphoid. Don't let it confuse you. We're talking about the same thing. So what does it do? It returns fluid into the tissues. So when fluid is in the tissues, we call it interstitial fluid. And it returns that fluid into the tissues and plasma proteins back into the blood. Think swollen ankles, that's interstitial fluid. The way it goes out, the way the fluid goes out is through the lymphatic vessels. So it doesn't go straight into the blood. Through these vessels, it goes all the way up to the neck, actually to the subclavian veins specifically, and dumps back into the circulatory system there. Once interstitial fluid enters the lymphatic, we don't call it interstitial fluid anymore. It's now called lymph. So together with lymph organs and tissues, we have a structural basis for the immune system. And that's why we are combining this whole lecture into the lymphoid or lymphatic and immune system lecture. So this is a quick picture of how the lymphatic system works with the arteries, the capillaries, and veins back to the heart. So over here in the top left picture, you see that lymphatic capillaries, blood capillaries, how it goes up into the heart from the venous system, arterial system, etc., etc. So you've got all of these capillaries coming in from the arteries. So red just means that they are oxygenated. So when you see these red capillaries, we're talking blood capillaries. The green is where we start talking lymphatic capillaries. So anyways, you have oxygenated blood and fluid coming in here from this arrow. And it leaks out into these tissues that surround it. So once it leaks out into these tissues that surround it, the lymphatics in the neighborhood, so these green guys, pick up the fluid and shortcut it straight back up to the heart. So that's what you see here. So this is a zoomed in version of this. Lymphatics are taking it and shoop, shortcut. So blood capillaries go to lymphatic capillaries. We have large collecting vessels with valves. We have little lymph nodes, these little dots. We have lymphatic trunk. So that's this guy in the middle. It connects. Remember, trunk just means it's going to branch out. Lymphatic ducts, moving up, and then back into the heart. So the lymphatic vessels, aka lymphatics, aren't made the same way a capillary is, but it's about the same size as a blood capillary. So that's the bottom picture over here. If you look closely, there are little flaps. It's flap-like mini valve over here. It's not a solid wall. And to keep it from collapsing in on itself, it's got these little filaments right here to tie to the connective tissue and prevent the lymphatic vessel from collapsing in on itself from either the tissue weight surrounding it or the cellular fluid around it. So this is where the lymphatic, where the fluid originally gets into the vessel, is through these little gaps, these little flaps. And then again, once it's inside, once that fluid's inside, we call it lymph. So outside of the lymphatic vessel, it's called interstitial fluid. Inside of the lymphatic vessel, it's called lymph. So this is a one-way flow towards the heart. Easy enough to remember since there's really nothing that goes against the heart, so everything's going to flow with the heart. As I touched on in the previous slide, the lymph vessels include the lymphatic capillaries, lymphatic collecting vessels, lymphatic trunks, and lymphatic ducts. So those are all the different kinds of vessels going from small to large. Smallest being capillaries, largest being trunks of ducts. So we've already talked about this in the image on, not the previous slide, but the one before. But here we go again. So lymphatic capillaries are very permeable. They can take up a lot of things because they have big giant flaps, even though they're tiny little capillaries. Still think of them as big flaps on these capillaries. So they can engulf even whole cells. So whole cells can get under those flaps and into the lymphatics. There's one thing that really differentiates a lymphatic capillary from a blood capillary. In blood capillaries, you can't get anything big in or out, whereas in lymphatic capillaries, we can take up cell debris, we can take up pathogens, which is really important, especially with immunity. We take up cancer cells. We take up a whole bunch of fluid. And that's its biggest piece, is taking in that fluid that we call lymph, right? It's called lymph once it's inside the lymphatic capillary. So lymphatic capillaries cannot actually be found everywhere in the body. They are not found in bones. They're not found in teeth. They're not found in bone marrow or in the central nervous system, the CNS. So remember, CNS is the brain and the spinal cord. Lacteals are specialized lymphatic lymph capillaries, and they're found in the interstitial mucosa. So the interstitial mucosa is the lining of the intestines, and these are special. They are made to absorb digested fat and deliver that fatty lymph to the blood. So think about what delivering fatty blood to the heart might lead to. Lymphatic ducts. So moving from small to a little bit larger, started with the capillaries, now we're at the ducts. Lymph is delivered to one of two large ducts. So we have the right lymphatic duct and the thoracic duct. The right one drains the upper right arm, the right side of the head, and thorax, aka chest cavity. Whereas the thoracic duct comes from the cisterna chyli, which you'll see a picture of in a second, and it drains the whole rest of the body. So the right duct only gets about a quarter of the body, and the thoracic duct drains the other 3/4 of the body. And each one empties lymph into venous circulation at the junction of an internal jugular vein and a subclavian vein on its own side of the body. So right lymphatic duct's going to be on the right side, so right internal jugular and subclavian veins. And then the thoracic duct, the opposite of that. So if you remember, right lymphatic duct is the right upper quadrant, you're going to know that the thoracic is going to be everything else. And, you know, dump that on the opposite end. So here is a picture of that. If you look closely, right where the internal jugular goes up and the right subclavian comes out, that junction, so on each side, here's one junction, here's another, is where the lymphatic duct will dump in. So the thoracic duct enters on the patient's left side. And sometimes if you feel puffy right above your collarbone, like you already so if you feel puffy at the collarbone and you already have swelling somewhere else in the body, let's say your ankles are swollen, we're going to use ankle swelling a lot as an example. It usually just means that you have a lot of interstitial fluid that all of a sudden is moving back into the system. So, once it's back in the system as lymph, it's all of it comes all the way back up and into these collecting ducts, right? So if you had a lot of swelling somewhere, it's moved up the system. It just gets a little backed up when it's pouring into the corners of these junctions. So you can get a little bit puffy up there under your collarbone until everything can get drained out. So you might not necessarily have done anything to cause swelling there. Maybe you have swelling somewhere else, and as a result, that will get a little puffy too. So the body is really interesting when it comes to these different things. But anyways, we're coming from a lot of places in the body and trying to drain into this junction between the internal jugular vein and the subclavian vein on both sides of the body, right? So a lot of swelling moving back into the system. You'll have some swelling up there as well. Nothing crazy, nothing dangerous. So how does the lymph actually move up your body? So a couple of things. If you'll remember from the circulation lecture, arteries pulse. So remember, arteries are full of smooth muscle, and the smooth muscle pulses, it squeezes. So as those arteries squeeze, the lymphatic vessels that are right next to them are also going to feel some of that. So it's going to help move lymph fluid along as well, just from its proximity. The walls of lymphatics have some smooth muscle, which also helps, but not as much as artery walls. And if you'll remember, artery walls are very, very thick as well. You've also got skeletal muscle, which helps. So if your ankles are swollen and you need to drain the ankles, the calf muscles will help pump that up. And we discussed that in a previous lecture as well. Remember back to the vasculature lecture, the calf muscles help bring everything back up. Venous return, for example. But anyways, if you're having swelling in your ankles, walking around can help that to drain as well. So those muscles contracting and relaxing can help drainage. Fun fact, if you are experiencing drainage issues from some other things, so let's say you have some varicose veins, so you remember how those can get lumpy and they won't do very well with pumping, you can actually prop your feet up higher than your heart, and that'll help your lymphatic system drain. So there is something to that. Lymphoid cells. So lymphocytes are the main warriors of the immune system, and we have two types. We have T cells, or T lymphocytes, and we have B cells, or B lymphocytes. We'll talk about these specifically during the later half of the lecture, but just remember B cells, blood. So B cells, blood. The T cells and B cells protect against antigens, so anything in the body that's perceived as foreign, they will attack. Whether it's bacteria, toxins of bacteria, viruses, red blood cell mismatches, like you got the wrong transfusion by accident. Hopefully that never happens to you. Cancer cells, the T cells and B cells recognize as not belonging. So you don't belong, you got to get out of here. I recognize you. I'm going to fight you. That's what the T cells and B cells do. The T cells manage the immune response and attack and destroy foreign cells, where the B cells produce plasma cells that secrete antibodies that then fight against the invaders, and B cells are in the blood. Lymphoid tissue. So those are clusters of lymphoid cells. They house and provide proliferation sites, so places for lymphocytes to grow and mature. and they furnish a surveillance vantage point. Think of this as a security office with footage of all areas on a campus, for example. Once a problem's recognized, that security then sends the guards or the troops to that spot so that the T cells and B cells aren't in the wrong place. But they will stay sequestered until it's go time. So the T and B cells, they really need to know exactly where to go. And that's what this proliferation site does. There are two different kinds of lymphoid tissue. We have diffuse lymphatic tissue. So this is where lymphocytes are scattered rather than clustered. And we have lymphatic follicles. You'll also hear lymphatic follicles be referred to as lymphatic nodules, where lymphocytes and macrophages congregate in really dense masses. So diffuse lymphatic tissue, scattered, dispersed, rather than clustered, and lymphatic follicles, we are clustered, we're congregating in dense masses. So lymph nodes. Lymph nodes, you probably recognize the term, like I said, but these are the principal lymphoid organs of the body. Lymphoid, lymphatic, same thing. So like I said, you're going to see both. Don't get confused. Lymphatic organs, lymphoid organs, talking about the same thing. Sometimes, so think of this as sometimes you'll get a knot or a little ball that you can feel up in your neck or your armpit. If it's in an armpit, we call it an axillary lymph node. Maybe you can feel a little round ball under your chin. In breast cancer situations, you'll feel big knots that come out of the armpit, out of your axillary lymph nodes. The ones that are closest to the surface will pop out pretty easily and noticeably. And think of your doctors, checking your lymph nodes. But we'll talk about that in a second. What does a lymph node do? So first and foremost, they filter lymph. Monocytes turn into macrophages and they destroy microorganisms and debris. So all the trash that needs to be filtered out, they take care of. They can't pump it back to the heart. They gotta cleanse it first and pump only the fluid back to the heart. Secondly, they work as part of the immune system. So lymphocytes are activated and they mount an attack against antigens or invaders. An antigen, you'll hear me refer to it as a foreign name tag. So an antigen, think of it as every cell having a name tag. And then the body knows which name tags are supposed to be there and which ones are not. So they will activate the bouncers, if you will, to remove the party crashers, the name tags that aren't supposed to be there, to remove and keep what needs to be there, and what's going to hurt you out of there. So this is a longitudinal view of a lymph node, what it looks like if you cut it sideways. If you remember, efferent means exit. So efferent, going out, exiting. Don't have an easier way to remember afferent, except for that's the other one. So if you remember that efferent is exit, you'll know that afferent is the one coming in. So E, exit, A, coming in. Let's see. You have a cortex and a medulla. So cortex is right here. Medulla right here. Remember that cortex is the outside, medulla is the inside, just like on the adrenal glands. And then if you'll notice on this longitudinal view of a lymph node, you have more incoming afferents than you have exiting efferent lymphatic vessels. And that's important because it slows the flow down to allot time for filtration to occur. Otherwise, you won't have enough time to filter anything out of the fluid. So you've got a bunch of afferent lymphatic vessels coming in that outnumber the efferent vessels coming out to slow everything down, so that all the junk you want comes out and only the clean fluid, all the junk you don't want gets taken care of and only the clean fluid comes out. Sometimes lymph nodes will swell up if you have some kind of infection. So now that you know that there are more entrances than exits, think of it as you have to filter out a bunch of bacteria. So you have more material being added to the lymph node that's going to cause it to swell up big enough that you can actually feel it with your fingers. Think about when, like I said earlier, think about when a doctor feels for swollen lymph nodes when you come in while they're giving you an examination. And that's what they're looking for. Circulation of the lymph nodes. Lymph is the fluid. It comes in through the afferents and exits through the efferents. There are less efferents to allot that cleanup time we just talked about in the previous slide. So this is just what we talked about written out. You can read through it. Okay, we're going to move on and talk about some organs involved in the immune system and the lymphatic system. So what does the spleen actually do? So it stores the breakdown products of red blood cells. It takes up red blood cells, breaks them down, keeps the parts that are reusable, and recycles the parts that aren't. It sends those back to the bone marrow where they can be used again to make new red blood cells. So reduce, reuse, recycle in the body. There is very little waste. If there is waste, it's coming out in the toilet, right? They also store blood platelets. In fetuses, spleens make red blood cells. Red blood cells are made in the spleen, the same thing, but it stops when you're born. Spleen also has a fibrous capsule outside and trabeculae inside. So remember trabeculae, they're just little cross beams, little cross channels. And these contain lymphocytes, macrophages, and huge numbers of erythrocytes, red blood cells. So all in the spleen, lymphocytes, macrophages, erythrocytes. Okay. The spleen is this big reddish brown organ. It can get much, much larger, especially if you have a blood disorder or something that's breaking your blood cells down early. The spleen can actually get as ginormous as your liver. The spleen is tucked away in your left upper quadrant, right below your diaphragm. So notice the kidney right there, the little adrenal gland that sits on it like a hat. That's just a good idea to give you an idea of where the spleen kind of sits. You also have this ginormous artery right here going into the spleen, the splenic artery, if you will. If you break a rib, it can poke a hole in the spleen, which is bad because there's so much blood flow to the spleen that it could cause you to bleed to death. Laceration to the spleen can cause you to bleed to death, which is not great. Important organ. Talked about the thymus a little bit in the endocrine lecture, but the thymus is another lymphoid organ. It is huge as you're a baby or in your youth, but by age 2, which I understand that's still your youth, but anyways, it's huge when you're a baby. By age 2, the thymus is going to stop growing, and then as you age, as you get older, it's going to atrophy. So it's going to decrease in size. It's going to shrink in size. And huge when you're little, atrophies with age. The thymus also makes T cells. So remember T cell, thymus, T cell, thymus, T cell, thymus, B cell, blood. Okay. So the thymus differs from other lymphoid organs in a couple of ways. It functions strictly for T cell, like I just said, or T lymphocyte maturation. It doesn't fight directly against antigens. The thymus is the T cell factory, rather. Tonsils are some of our simplest types of lymphoid organs. And there are actually a lot of different types of tonsils. There are 4. So I know most of us know of one, but we're going to talk about each type. So we have the palatine, that you can see when you open your mouth, and those are the ones that most people will get removed. Some of you guys probably don't have your tonsils anymore, but that's just one type, and those are ones that we're used to. Those are ones you can see when you open your mouth. Lingual tonsils are on down your throat at the base of your tongue, so your tongue actually stops a couple inches down your throat, and that's where the lingual tonsils are located, at the base. Pharyngeal tonsils are up behind your nose, and then your tubal tonsils are right at the ends of the auditory tubes, also called the eustachian tubes. So what's bad about those? If those get swollen, your eustachian tubes, then it closes off, or your tubal tonsils. If your tubal tonsils get swollen, they will close off the ends of your eustachian tubes. So why this isn't that great? It causes fluid to build up in your ears. And if there's any bacteria there, now you've got a middle ear infection, all because you can't drain the fluid out from your tubal tonsils being swollen. These tonsils actually also get surgically removed sometimes in people that are having chronic middle ear infections, because too many will cause hearing loss. So I don't know if you learned about auditory cilia, but if you lose your cilia, they will never grow back, and that's how you hear. So too many ear infections can cause cilia loss, cause hearing loss, and then surgery ends up being the only solution to get these tubal tonsils removed. Here's an image of the location of 3 of those. Tubal's not shown here, but the pharyngeal tonsils, if they are swollen, you feel like you're swollen up behind your nose. That's called pharyngitis usually, not laryngitis, because the pharynx will be swollen. Palatine are the ones you can see at the back of your throat. Of course, if you still have them, you can see them if they haven't been surgically removed. And then the lingual ones are all the way down your throat, right there at the bottom. So tonsils, they don't have capsules like lymph nodes do. They just have epithelial tissue covering them. So what it means, what this epithelial tissue overlying tonsil masses invaginates, forming tonsillar crypts. So what this means, tonsillar crypts, everything's got nooks and crannies. And those nooks and crannies, the invagination, those nooks and crannies, those are the tonsillar crypts. What happens is bacteria and other junk can get caught in those little crypts, little openings, and that will activate the immune system. The immune system will fight off that bacteria, and then what's left over is going to be that white pus chunky spot that you see during tonsillitis or after tonsillitis, after you've already healed up, and you can actually remove those chunks with a Q-tip. The end products are pretty solid. When I say solid, I mean actual solid pieces. You can get a Q-tip and pop it out. So we touched on lymph follicles. Let's talk about them a little bit more. They are not standalone organs. They are patches of lymph tissue that are found inside other organs. Peyer's patches are clusters of lymphoid follicles in the small intestine and appendix. So they destroy bacteria and prevent it from getting through the intestine wall. If you have bacteria coming through the intestine, which is normal, you don't want it to be reabsorbed through the wall. So remember, we have a bunch of capillaries that line our intestines. You don't want that bacteria to go into the capillaries and then back into the body. You want it moving through your body and out of your body into the toilet. Peyer's patches are what help keep that working like it's supposed to. Other than the spleen and tonsils, lymphoid organs are poorly developed at birth, so they grow over time. Not the thymus. The thymus is going to grow until you're 2, then it's going to stop growing and atrophies. So we're not talking about the thymus here, but other than the spleen, tonsils, rest of your lymphoid organs are going to grow over time. Um, Breast milk is really important for newborns. If they are on breast milk, they're getting their mom's T cells and B cells since they can't really make their own yet. At birth, the three biggest things for newborns are: does your brain work? Do your lungs work? Does your heart work? Everything else kind of develops as you go, as you age. So now we are moving on to immunity, which is the resistance to disease. We have two different categories here of immunity. One is the innate, the non-specific defense system, and one is adaptive, or the specific defense system. So non-specific means very broad, very generalized, doesn't fight a specific pathogen, whereas adaptive is the opposite. You're fighting a particular pathogen, you know what you're exposed to, and that is what you are fighting. So this happens when you're exposed to something really specific, your body develops a defense against it, or you take a vaccine for a particular pathogen. And we're going to get into the details of what all of those entail. The rest of this lecture is only going to focus on immunity. So innate, specific, and then, innate, generalized, and then adaptive, specific. So what comes under the innate defense category? Innate, general, broad-based. Skin is going to be the first surface barrier. And there are so many diseases that your skin keeps out just by existing, just by being there. Anytime that you cut yourself or breach the skin in some way, even with dry skin that has little micro cracks in it, it can lead to some kind of infection, because anything can get into your system from those little cuts, from those little spots, get inside of you. So skin's your first defense. Mucous membranes, these are the linings of your nose, your eyes, your mouth, linings of the digestive system. And these create a mucus that keeps you from some of the diseases that your body can get exposed to, that your body can encounter. Then we move on to internal defenses. So the surface barriers were skin and mucous membranes. Then we have the internal defenses of phagocytes, NK cells. These are our natural killer cells, coolest name ever. Inflammation, antimicrobial proteins, and fever. And all of these are generalized, broad, not specific. Innate are broad, not specific. But we move on to adaptive, where we do have a very specific response defense. Humoral immunity, that is your blood, B cells. Remember, B cells, blood. Why is it called humoral? So just a fun little story. In ancient times, if you will, if somebody was sick, it was said that they had bad humors. So what healers would do back then is, if something was wrong with their humor, something was wrong with their blood, these healers would use leeches on a patient, or cut that patient and let them bleed to get the bad humors out of you. So get the bad blood out. So yeah, humoral immunity, kind of stuck around that name. Humoral immunity, blood-based immunity. That's where your B cells come into play. Cellular immunity, T cells. So T cells fight within the cells and cellular immunity. And then our last one are APCs, antigen presenting cells, which we shall cover. In a second, we're going to cover all of these. Oh, we're not going to cover skin that specifically. We talked about it. But everything else we're going to talk about pretty specifically. So innate, internal. If somehow microorganisms get deeper, you need a defense mechanism, right? So this is where phagocytes come in. So they include macrophages and neutrophils. Our NK cells are natural killer cells. We'll have the inflammatory response, which includes macrophages, mast cells, white blood cells, which, you know, we looked at white blood cells a lot, and then inflammatory chemicals. We also have, number 4, antimicrobial proteins like interferons, call these INFs, interferons, and complement proteins. and then fever also. And we'll get to details in all of these, like I said. So first, but not least, phagocytes, specifically the macrophages. Macrophages develop from monocytes to become the chief phagocytic cells. So phagocytic cells are the Pac-Man of your blood. Phago means eat, cyte is cells. They engulf themselves around whatever they're going to eat, Pac-Man style, and they digest it and spit out the parts that they can't digest. And now, whatever bothered you is gone. It's been eaten by the phagocytes. There are two kinds of macrophages. There are free macrophages that wander through the tissue looking for something that doesn't belong there. And then there are fixed macrophages that stay in one place. They are permanent residents in some organs, if you will. Moving on to our second kind of phagocyte, we have neutrophils. They become phagocytic when they encounter infectious material. So usually neutrophils are just floating around the bloodstream, they're just hanging out. And then when they encounter something like bacteria or virus, they engulf it. So if you'll remember, neutrophils are the most abundant, the most numerous of all the white blood cells. And we've got a whole lot of them just hanging out in our bloodstream, waiting to protect us, to phagocytize what we don't need. So how does phagocytosis happen? Step 1, the phagocyte adheres to the pathogen. So it has to approach the bacteria or virus or whatever it is, and this is facilitated by a process called opsonization. So it attaches antibodies called opsonins to the surface of the pathogen. And antibodies are what recognize the invader, the foreign cell, the name tag that doesn't belong. In this case, these special antibodies are called opsonins or opsonins, and they act like homing beacons that attract the phagocytes. So not only will the phagocytes engulf the foreign cell, but they're attracted to the foreign cell by this coating of opsonins on the foreign cell itself, which is pretty neat. Got a picture coming up. Okay, so, sorry, let me get a drink of water. And so in this image, the purple part is the macrophage, and it uses its cytoplasm to make these purple tendrils coming off of it, these little squiggly lines over here. These purple extensions grab hold of the bacteria, which is this little green blob pictured here on each side. And the macrophage, using its cytoplasm like extensions, is going to wrap itself around the green part, the bacteria, and tuck it inside itself. So if you watched Star Trek, it works like the Starship Enterprise's tractor beams, shoots out, grabs the invader by engulfing it completely, and then pulls it inside of itself. Even if you haven't watched Star Trek, you can kind of imagine what that looks like. Here's another image of phagocytosis. Just looking inside, looking at what's going on the inside here. So to summarize what's happening in this slide, the green is the bacteria, the purple is the macrophage. So looking through this, remember from Anatomy 1, if it ends with ACE, it's an enzyme. So the green bacteria is being drawn into the phagocyte. The lysosomes go in, break it down. There are enzymes inside. The enzymes break down the bacteria into parts that they can digest, like eating a watermelon, spitting out the seeds. And then bloop, removes the seeds from the watermelon. You can read through these. Let's read through these. So phagocyte adheres to pathogens or debris. Phagocyte forms pseudopods. Remember, pseudopods are fake feet that eventually engulf the particles, forming a phagosome. The lysosome fuses with a phagocytic vesicle, forming a phagolysosome. The lysosome enzymes digest the particles, leaving a residual body, and then exocytosis of the vesicle removes indigestible and residual materials. So exactly what I said, but with a lot of fancy science terms. Moving on to our coolest named cells, our natural killer cells. Second type of innate cell. Super, super cool name. So they are very large granular lymphocytes. So a regular lymphocyte is agranular. Natural killer cells are granular lymphocytes. So this is a really specialized cell that doesn't fit into the normal category. So please, please, please don't let this confuse you. We learned the basics in the blood lecture, but this is way, way more specialized. So there are other rule breakers out there, if you will. This is one of them. So just remember that natural killer cells are granular lymphocytes. Just remember that. Don't let it confuse you. So all cells have an MHC, which is a major histocompatibility complex. It's an identification marker or name tag. Again, see, I told you we're going to use name tag a lot. But that's what tells you what kind of cell it is. Natural killer cells wander around, link up to one of these cells, ID them, and either say, you're good, move along, or nope, you don't belong here, kill it. So, pretty cool. So third part of the innate internal defense system is the inflammatory response. And some of the cardinal signs of inflammation are redness, technical term hyperemia, heat, calor. If you speak Spanish, calor is hot. So remember, also calories. So calor, heat, swelling, also known as edema, and then pain. And then also sometimes there's impairment of function as a fifth one. So this is if there's too much swelling, you can't move. We're going to use the twist your ankle example. You're going to hurt, you're going to swell, you're not going to be able to walk on that foot while your ankle's swollen. So this chart is really, really busy. But it shows you how all of this kind of happens. So how you get heat, redness, pain, swelling, joint limitation from inflammation. So start at the top. Tissue injury. You have tissue damage. You have a release of chemical mediators. Then several things can happen once the chemicals are sent out. You can have vasodilation. So your vessels open up. When the vessels dilate, they open up. It's going to make you more pink red from increased blood flow to the area. So there's your redness, right? Boom, redness. Also, think of summertime. Your blood vessels are dilated on the surface of your skin to release some heat. So you feel heat radiating off your face. That's going to hopefully increase the metabolic rate of cells and cause you to heal more quickly. So locally increased temperature increases metabolic rate of cells, promotes healing. So that's just one little branch off of tissue injury. The third one that can happen is your capillaries become more permeable, so increase capillary permeability. And leak fluid into the tissues, which becomes interstitial fluid. So it was plasma in the capillaries, it was lymph in the lymphatic capillaries, it's interstitial fluid outside of the capillaries. All this fluid in the tissues we would look at externally and see swelling. So boom, now we're down leaked protein-rich fluid in tissue spaces, we're at swelling. And if you're stretching those tissues, then you would cause pain. And that would lead to temporary limitation of joint movement to prevent further injury and promote healing. So stay off your swollen ankle, help it to heal faster, essentially. There's that. You can read through the other ones. That's just a couple examples. If you're reading through these, let's see. A margination of leukocytes. That just means white blood cells are rushing in, like with a cut or a gunshot wound. Leukocytosis up here, inducing factor, is also a call to white blood cells. So tissue injury, release of leukocytosis inducing factor, so a call to all white blood cells. Leukocytosis, so increased number of white blood cells in the bloodstream. Leukocytes are going to migrate to that injured area. Margination that we just talked about. They're going to pass through capillary walls. Phagocytosis is going to happen of the pathogens to tissue cells. The area is going to be cleared of debris. Pus may form. So remember we were talking about the tonsils. You can remove that little debris. Area is cleared of debris. Boom, promotes healing. You can read through the rest of these and see how all of that leads to the same stuff here. All these defenses are to promote healing as a result. So, number 4, moving on to antimicrobial proteins. So we just talked about interferons or IFNs. We have interferons and complement proteins. For me, it's easier to say interferon than IFN. I keep wanting to say IFN. So I'm just going to call them interferons. But we have those and we have complement proteins. They attack microorganisms directly and prevent them from reproducing or replicating. So one bacterium is not going to make you sick, but once that bacterium undergoes binary fission, which is just a fancy term for reproduction in bacteria, once it goes through binary fission and one bacterium divides to thousands, which divides to tens of thousands, which divides to hundreds of thousands, that is when you get sick. That's how you go from something super mild. One day you go to sleep and the next day you're super sick. That's what happened in your sleep. That bacterium just divided into a lot. But if you can stop them from dividing, then you're not going to get sick. So it's going to hinder the microorganism's ability to reproduce so that hopefully you don't get sick. We're going to discuss interferon specifically. So cells that are affected by viruses will secrete interferons to battle that virus. So the interferon will slip out and into neighboring cells and signal those neighbor cells that, hey, we've encountered a virus, be ready to attack. In this burglar example down here, sending the kid to the neighbors to warn them. Neighbors are waiting for the burglar with the police. The burglar is the virus and everyone else is the interferon. Interferons are made naturally, but you can also undergo interferon therapy where interferons are genetically created and introduced via injection. And that's done a lot with cancer treatments. Complement proteins are pretty sweet. They don't sound that cool until you learn about what they do. But there are about 20-ish blood proteins that circulate and stay inactive until they're needed. They kill bacteria by cell lysis, aka they blow them up. So here's what happens. The complement protein pokes holes, bunch of holes in the bacteria, and where there are big holes in the bacterium, fluids and salts enter into that bacterium in unlimited capacities until that bacteria swells up so much that it explodes. Dead bacteria can't divide or undergo binary fission or whatever. So, boom, you're done. Complement proteins just murder those bacteria for you. And then our 5th innate defense is a fever. When leukocytes and macrophages are exposed to different foreign substances, they're going to secrete something called pyrogens. We're not going to talk about this very specifically, except that pyrogens are going to trigger the hypothalamus to secrete PGE2, and PGE2 sets the body's thermostat. So if you are telling the hypothalamus to secrete PGE2, and it increases the body's thermostat, you are ergo causing a fever. So bacteria have a very, very narrow temperature bandwidth. If the temp is too low, they don't survive. If the temperature is too high, they don't survive. So a fever will cook bacteria, kill it, if you will. Unfortunately, it can also do this to your cells because your cells, too, only have a very narrow temperature bandwidth. So looking into that a little bit deeper, fevers are good to a point. So you do not want to denature your proteins. It is not good for you to denature your proteins. It's not good to denature enzymes. Think about frying an egg. Once fried, that egg is never gonna it's never gonna regain its original shape. Once you fry that egg is done. It is fried. It will never go back to what it once was. It's the same thing with your proteins. If you're at 102 degrees Fahrenheit and under, then you're in good shape. That is a moderate fever. There are benefits to it that we'll talk about. If you're at 103 degree fever plus, that is the danger zone. So you've got to get that temperature down. 103 plus is brain damage. It's brain damage territory. You're cooking your proteins. You don't want that. Ice baths will help lower that temperature. Alcohol on the hands and feet are going to help lower that temperature. So that's not just an old wives' tale. There is stuff to that. My parents did that to me as a kid. They would put alcohol on my hands and feet to help lower temperature if I had a fever. With kids, you want to be careful about giving them aspirin. You kind of want to stay away from aspirin to reduce fever because you can cause a problem with Reyes syndrome. Reyes syndrome in kids can cause swelling of the brain and liver, so we don't want to go down that path. Instead, we give children's Tylenol to reduce fever. Ice is going to be the best thing. Cold packs aren't under the armpits, on the feet, but don't do direct because you also don't want to cause frostbite. So always cover your cold packs with a cloth. But yeah, you want to get that temperature down. You don't want to be in the brain damage territory there. But let's talk about some good stuff. All right, so benefits. Benefits of a moderate fever. Moderate fevers can cause the liver and spleen to lock down the iron and zinc, which is what bacteria and viruses need for survival. And if they don't get it, then they die. Fever also increases the metabolic rate and speeds up repair. So it gets your lymphocytes to move faster and moves everything to the spleen faster too. So that's good. But you want to be under 102 and under. Remember, 103 plus is the danger zone. Switching over to the other half of the immune system, the adaptive immune system. So we're going to start with lymphocytes, and we're going to move on to APCs. B cells provide the antibodies. They fight the war in the blood. So B cells, blood. T cells are cell-mediated. They fight the war inside the cells. And then we have our antigen-presenting cells, our APCs. Just talk about APCs real fast. Antigen-presenting cells. So these bad boys, they engulf the bacteria. They get the antigen name tag off it, and they give that name tag to the T cell so that the T cell can read it. They know who the enemy is. Now the T cell can get ready for battle. So the APCs are the scouts. They capture some enemies, bring them to HQ, headquarters, and then headquarters can present their defense and offense, right? So APCs figure out the details, let the T cell know. The T cells figure out how we can get rid of this thing. If we need antibodies made by the blood, the T cells would let the B cells know to make antibodies. If that's not what's needed, then the T cells are going to launch a direct attack themselves. And that's basically what this slide is kind of showing you. Alrighty, that leads us to vaccines. So remember humoral immunity. Humoral is blood. You have active immunity and passive immunity. Naturally acquired active immunity you get with direct contact with a pathogen. You develop your own antibodies and you create your own immunity. Then over here you can have artificially acquired active immunity. So that's a vaccine. It can be dead or it can be attenuated. Attenuated means live. It means weakened, but it means live. It's not killed. We usually don't say killed either because viruses are not life, right? But for the sake of simplicity, alive and dead is easier than activated versus inactivated. But that's usually what we will say with viruses, that they're, or vaccines, activated, inactivated, when we talk virus. When we talk bacteria, we say dead and live because bacteria is life. They are alive. They have all of the components of life whereas viruses don't. Viruses can't survive without a host, and there's some other things there too. But anyways, okay, so active, we have naturally acquired and artificially acquired. Artificially active are the vaccines. And then on the passive side, we have naturally acquired through antibodies gained by a fetus within the placenta or by a newborn baby through mother's milk. And then there's artificially acquired through gamma globulin injection, which is a big, thick serum. So both of these, active and passive, we can get naturally or we can get artificially. All right, so vaccines. A lot of people think they know a lot about this, but most people definitely don't. So let's learn about it. There are 5 different kinds of vaccines and different ways that they are made. First, we have live attenuated. So the pathogen is live but weaker than original. So you introduce a weaker form of a pathogen that your body can fight more easily, develop immunity. And then if you ever encounter the full strength guy, the full strength pathogen, your body will recognize it and you already have an immunity to it and you're going to be good. Or at least you're not going to be as affected by it as badly as you would have been without that vaccine. These aren't used as much anymore because there is a small downside that the virus can mutate and become active again. Very good example of a live attenuated vaccine. And remember, when we talk vaccines, we're usually talking about viruses, but there are antibacterial vaccines. One of the more popular ones, it's not really used anymore, but it's called BCG, and that's used to prevent tuberculosis. Tuberculosis is bacterial. BCG is a live attenuated vaccine to prevent against tuberculosis. So before I was born, I'm from Europe originally. Before I was born, my parents actually got the BCG vaccine. So now if they have to do a tuberculosis skin test, it's always going to show a positive because that vaccine still, that attenuated vaccine is still in their system. So on a TB skin test, they're always going to show a positive. So what happens is that they have to actually get their lungs x-rayed to show that they don't actually have tuberculosis. But yeah, that is caused by that attenuated vaccine. The good news is they got this vaccine over 30 years ago and they never got tuberculosis. So, there's a reason for these guys too. And pretty cool story. So that's live attenuated. So weakened form of the original pathogen. And then we have killed or inactivated. Like I said, we like to say inactivated in science because a virus is technically not alive. Bacteria are alive. Viruses are not alive. They are not technically cells. And one of the tenets of cell theory is that the cell is the most basic unit of life. And again, they can't survive. Viruses cannot survive without a host. Bacteria can survive without a host. But anyway, you don't need to know all that for this class. If you take more biology classes, microbio, for example, you will have to know this. But anyways, inactivated, it's been heat treated or chemically treated to be inactive, and it can never become active again. It can never reactivate. So these are pretty solid vaccines, used a lot. The third type is recombinant. So this is a genetically engineered vaccine to create a protein that the immune system can target. So you don't have a whole working copy of the pathogen like in the previous two, rather just protein recognition software should you come into contact with the actual pathogen. So that's what the recombinant piece is. So think genetically engineered, think protein recognition software. Fourth type is a protein subunit. It's a piece of a protein with a little bit of antigen. Remember the name tag, antigen on it. This is what I am. And it tells your body when you get the vaccine what kind of pathogen it's encountering. And you can fight it like it's the full-blown real deal, right? And then our fifth type, last but not least, conjugate. So a lot of researchers, a lot of scientists would say that conjugates are the best and the strongest vaccines out there. This is great for everybody except for immunocompromised people because their immune system is not going to be able to take it. Whereas the rest of us, us who are not immunocompromised are going to want this one. Strongest, bestest. Bestest isn't the word, whatever. They're the strongest vaccines out there. So they use a protein and they use a piece of either the bacterium or the virus, whichever, whichever vaccine we're getting to fight whatever, whether it's bacteria or virus. So it's going to be stronger than the recombinant or the protein subunit. But like I said, vaccines are usually viruses. One of the BCG is one of the live attenuated bacterial vaccines that you see, but typically you see vaccine, you think virus. I did post this table, so you should have this Excel spreadsheet under this week's materials. But you'll find this slide. We'll give you a list of the most common viruses and types of vaccines you get for them. It'll tell you the virus side effects too, contradictions, but it's a pretty cool chart. So virus over here on the left, the incidence rate, what we're still seeing, something that can happen, some of the effects, the type of vaccines, whether it's live, attenuated, inactivated, protein subunit, killed, protein only, protein subunit, conjugate. Influenza is live attenuated. So with the flu shot, if you're already sick, it's going to make symptoms worse. So people that are like, oh, the flu shot made me sick. No, you're already sick. You already had the flu. You got the flu shot kind of late, so it just kind of made it worse for you. But that's what's happening there, which is pretty neat. So yeah, you can read through this. Pretty cool, pretty informative. Most of the general public never pays attention to stuff like this. They just listen to what's going on in the media, but we need to learn the science behind it, right? So moving on to antibodies. We have immunoglobulins, which is a special protein antibody. They're proteins that are secreted by the plasma cells, and antibodies are capable of binding specifically with antigens detected by B cells. Remember, antigens are name tags. We have some classes of antibodies. There are different types of immunoglobulins. Anytime you see IG, you know that you're looking at an immunoglobulin. IgM, immunoglobulin N. M is the first antibody released, and they're going to clump anything that doesn't belong. We have IgA. That's found in secretions like mucus, snot, phlegm that helps prevent entry of pathogens. So it's not only a physical barrier, but it's got the IgA, that mucus, that snot isn't only a physical barrier, it also has the IgA in it. So any pathogens that are captured by that mucus, IgA can take care of, can kill, can neutralize. IgD is a monomer attached to the surface of B cells. That's all you need to know there. IgG is 75 to 85% of antibodies in the plasma that can cross the placenta into the baby, so that they can get a little bit of immunity from their mom before they're born. So IgD, monomer attached to surface of B cells. IgG, 75 to 85% of antibodies in cell and crosses the placental barrier. Then we have IgE. So immunoglobulin E is going to be active when you have allergies or parasites. It can cause mast cells and basophils to release histamines. So IgE symptoms are going to be histamine type symptoms like allergy symptoms without the anaphylaxis. Here we're talking itchy, watery eyes, scratchy throat, runny nose. We're talking sinusy, head cold, upper respiratory allergies. IgE is responsible for those. So all of our defenses are antigen-antibody complex. So we have neutralization up here on the left. These are the ways that we can inactivate these things. We can neutralize bacteria, viruses, exotoxins by attaching antibodies to the surface of these toxins. We have agglutination. So cell-bound antigens, we can clump them up so that they can't go anywhere. And we have precipitation, soluble agents. So we can precipitate them, and this means we are ensuring that they cannot dissolve. So think bladder infection. Bacteria have precipitated in urine. Phagocytes kick in. Inflammation happens. Histamines release, and once that stops, it can't hurt you anymore, right? So over here, phagocytosis, boom, like we talked about earlier with those images, and inflammation response, histamine release here. So neutralization, agglutination, precipitation are the inactivation half of the antigen antibody complex. And then on this side, on the right side up here, we have the fix it and activate side of the antigen antibody complex. So this is where we explode the cells, right? The complement side that lead to blowing up the cell. But again, no more bacteria. We're done. We fixed it. These are going to be just really, really basic definitions of organ transplant. We are not going to talk about this very specifically, except for in terms of the 4 different types of ways that we can do transplants. And then we're going to talk about prevention of rejection. So organ transplant, basic definitions, 4 varieties. We have autografts. Anytime you see auto, you know self. So think about a bad burn and skin grafts. So if you have a bad burn, doctors are going to take skin from one of the parts of your body and put it on your burn to help promote healing. So autograft, self. Isografts are between identical twins. And then allografts are between anybody who is not an identical twin. So allograft could be between another family member or a complete stranger. Then we have xenografts. Anytime you see xeno, think alien. Okay, so xenografts from another animal species. If you have a giant, huge burn and you don't have enough skin to take from a different part of your body and do an autograft, sometimes doctors will use pig skin. Now, obviously, that pig skin has to go through like a whole bunch of, science and cleaning and everything to get it to where it can be used in a xenograft. But that is what happens if you have a gigantic burn and not enough skin from a different part of your body to help do an autograft, right? Xenografts will happen there. But like I said, we're only touching on transplants and how they relate to immunity. We're not going to get into specifics. If you go into specialized medicine, you will have plenty of classes and learning to do regarding transplants, but not in this class, just touching on it. But finally, prevention of rejection. So if you're going through the time, the money, the waiting for an organ transplant, the one thing you don't want is for your immune system to think invader and reject that transplant. So you have to go through extensive testing. Your donor also has to go through extensive testing, and your donor, has to go through all this testing to ensure that they are compatible with you, right? One way doctors can help make sure that your immune system doesn't attack the new organ is through immunosuppressive therapy. So we just talked about your immune system, your immune response, how your immune system builds, what it does when it sees invaders. Well, if you have a new organ coming into you, that's not something that's already existed. Your immune system is going to see it as an invader. And you don't want your system to reject it. So it's good to prevent rejection of the new donor organ. But the pitfall is that your immunity is going to be reduced with immunosuppressive therapy, right? You don't want to reject your new donor organ, but by taking immunosuppressive therapy, you're going to become more susceptible to getting sick than the average person. So it puts you into this immunocompromised state. So when people get quarantined after these types of transplants, that's why. It's to ensure that no loved one comes to visit, and they don't know that, they might have a common cold. They don't know that they just picked up the flu on a door handle and they come into this room and they cause a pathogen that somebody's your immune system would have easily taken care of. But now, because you're immunocompromised, you're in this immunocompromised state, that small pathogen that your immune system could have taken care of has now killed you, But that's why people with transplants are usually quarantined from other folks. Like it's not in any hateful way. It's to make sure that uh, that immunocompromised person with this brand new organ um, stays quarantined so that they're not exposed to anything that could be detrimental to their livelihood. Some people with transplants have to take immunosuppressors for the rest of their lives. Others only have to take them for a little while until their immune system figures it out, right? Figures out the new organ. All right, cool. You're good to stay now, you know? It just depends on the person and the immune system, etc., etc. But that's it. That's it for our lymphatic and immune system lecture. So some new stuff, you know, that you may not have heard of before, but pretty cool. Pretty cool the things that your body does.